Electromagnetic radiation was supposed to contain waves. Some phenomena like diffraction and interference could also be explained by the wave nature of such radiations. But some phenomena couldn't be explained by the wave nature of electromagnetic radiation. The two main phenomena were blackbody radiation. A body is said to be a black body if it absorbs all type of radiation incident on it and nothing is reflected. The nature of emission from black body is called blackbody radiation and could not be explained by the classical theory of radiation put forward by Rayleigh and Jeans, which says I equal to 2 pi CKT divided by lambda to the power of 4, where I is the intensity of radiation at a particular temperature T, C is the velocity of light, K is the Boltzmann constant, lambda is the wavelength of radiation. So, from this equation it may be said that at low wavelengths, intensity of radiation should be large, like this. But experimental results show that there is a dip in intensity below the visible region, that is, in the UV region. This was named UV catastrophe. Planck suggested that radiation of any wavelength cannot be emitted by the body. Only certain discrete amount of energies are radiated or absorbed, like this. These dots represent what is called quantum, and the energy of a single quantum is directly proportional to the frequency of radiation, such that the energy of a quantum E equal to h nu, where h is known as Planck's constant, which is equal to 6.6 into 10 to the power minus 34 joules second, and nu is the frequency of quantum in hertz. Quanta are available only for selected wavelengths and not all wavelengths, but it may correspond to frequencies either in the UV region or the visible region or the IR region of the spectrum. One thing is for sure, that a single quantum of the UV region has more energy than a single quantum of the visible region, which is again of more energy than a quantum of the IR region. Now, to explain the actual picture behind it, I will separate these available quanta like this. The quanta that fall under UV region is this, and the quanta that fall under the visible region is this, and these quanta fall under IR region. What we see that only a few quanta are available in the UV region. This accounts for the reason why there is a dip in the curve over here. The available quanta in these two regions are more or less the same. This accounts for the fact that why classical laws of radiation match with the observed results up to this point. Now let us look at the wavelength versus intensity curves at different temperatures. Of course, the maximum quanta available at this temperature come from the visible region. The wavelength of the maximum available quanta is called lambda max. The lambda max at a given temperature is given by Wien's displacement law, which is lambda max into T equal to B, which is constant, and its value is 2.9 into 10 to the power minus 3. At lower temperatures, it is in the IR region. That is the reason why no glow is visualized by hot bodies below a certain temperature. At higher temperatures, this lambda max or color equivalent to lambda max is shifted from red to orange to blue and finally to white. Photoelectric effect. When metals like potassium, rubidium and cesium are exposed to a beam of visible light, electrons were ejected from the metal surface. This phenomena was called photoelectric effect. At first, this beam of light was thought of as waves. As you see here, that blue light of low intensity is falling on this plate coated with potassium and electrons are ejected from the plate. When the intensity of the beam was increased, more electrons ejected because the energy has increased. Now the wavelength of light is changed to make the light beam red. But it was seen with red light that even if the intensity of red light was increased several times, it could not eject a single electron from the surface of the potassium metal, which only a low intense blue light was able to do. This means that the frequency of light beam had something to do with this phenomenon. It was actually observed that electrons could only be ejected from the metal surface with light beams exceeding a certain minimum frequency, which is called the threshold frequency. Different metals have different threshold frequency. Quantum theory was used to explain this phenomena. Light beam was believed to consist of small particles called photons, and each such particle was thought of as a single quantum with energy equal to h nu. An electron on the metal surface can be interacted or touched by a single quantum at a time. You see that there is no space for two quanta hitting this electron. Therefore, the total energy of the entire quantum is not a factor. This explains why red light cannot eject electrons from the surface of potassium, however bright or intense it may be. On the other hand, only a low intense blue light can do the job, because the energy of a single quantum of blue light exceeds the energy of an electron on the surface of potassium metal. Now, explanation of these two phenomena confirmed that electromagnetic radiation can be thought of as consisting of very minute particles, as well as it can be thought of as waves. This gave rise to the concept of dual behavior of matter. The energy of a quantum was equated with the energy got from the famous mass-energy relation formulated by Einstein, E equal to mc square. What we get? We get lambda equal to h divided by p, where p is the momentum. This relation was assumed to hold good not only for photons but also for microscopic particles like electrons. This was proposed by French physicist de Broglie.